A 3-node Raft cluster in Kubernetes kept losing its leader every few minutes. Writes failed with no leader errors. The root cause? Each node had only 4 GB of RAM and the Raft log grew unbounded because we never set a snapshot threshold. When memory pressure hit, the OOM-Killed the process. The node restarted, rejoined the cluster, and the cycle repeated. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover distributed consensus, Paxos and Raft. Distributed consensus ensures that a set of nodes can agree on a single value even if some fail. It's the foundation of replicated state machines used in databases and coordination services. Before consensus, systems used heartbeat-based failover. If the primary is slow, a backup takes over and you get split brain, 2 servers accepting writes, diverging data. Consensus solves this by ensuring at most 1 leader. Here's a simulation of split brain without consensus. 2 nodes both think they're primary, and clients write to both. When the network heals, data is inconsistent. With Raft, only 1 leader exists, preventing this. Paxos is the gold standard but notoriously hard to implement. The original paper describes single decree Paxos. Multi-Paxos extends it to a log, but the protocol is underspecified. Every production system uses a custom variant. Here's a simplified Paxos single decree. A proposer sends prepare requests with a unique epoch. If a majority promises, it sends accept. If a higher epoch proposer appears, it must reuse the same value, preserving consensus. Raft decomposes consensus into leader election, log replication, and safety. It always has a strong leader that handles all client requests. Randomized election timeouts avoid split votes. Here's Raft leader election in action. Node A crashes. B's election timeout expires first. B requests votes, gets a majority, and becomes the new leader with a higher term. Once a leader is elected, it replicates log entries via append entries RPCs. A follower appends and replies. The leader commits when a majority stores the entry. If the leader crashes, the new leader will have the committed entry. Here's a log replication example. The leader sends an entry, 2 followers acknowledge, and the leader commits. Even if the leader crashes, the new leader will have this entry. Consensus guarantees safety, but not liveness. Raft avoids live lock with randomized timeouts. During a network partition, the majority partition can make progress. The minority is unavailable. In a 5-node cluster split into 3 and 2, the majority partition can elect a leader and make progress. The minority cannot. When the partition heals, the minority steps down. No data loss. Consensus is synchronous. To improve throughput, batch multiple entries into a single append entries RPC, use pipelining, and parallelize disk writes. For higher throughput, shard across multiple Raft groups. Batching entries halves the number of RPCs. Pipelining sends the next batch before receiving an ACK, but must handle out-of-order commits. Consensus is expensive. If you need high throughput or low latency, consider alternatives like leases, gossip protocols, or CRDTs. Use the simplest solution that meets your consistency requirements. Here's a decision rule. If you can tolerate eventual consistency, don't use consensus. For low write volume, consensus is fine. For high throughput, consider sharding or alternatives. This is the same issue we highlighted at the start. Here's exactly why that happened. Each node ran in a container with only 4 GB of RAM. The Raft log grew unbounded because we never set a snapshot threshold. When memory pressure hit, the OOM-Killed the process. The node restarted, rejoined, and the cycle repeated. The fix was to set a snapshot threshold. In etc., that's snapshot count equals 10,000. We also increased the memory limit to 8 GB per container and configured log compaction to keep the log under 500 MB. This prevented OOM kills and stabilized the cluster. Without a snapshot threshold, the log grows unbounded, leading to memory pressure and OOM kills. Always set a snapshot threshold in production. Using an even number of nodes, like 2, means a single failure causes loss of majority. Always use an odd number, 3, 5, or 7. Don't allow followers to serve reads without the leader's approval. The leader must confirm it's still the leader via a heartbeat round to avoid stale reads. The article describes Raft's leader election and log replication generically, but production implementations like etc. v34+, and console v18+ have specific behaviors. For example, etc's experimental initial corrupt check flag can detect log corruption at startup. Always check the documentation of your specific Raft library for version-specific quirks. The article mentions that the leader forces its log on followers after a crash, but doesn't show the concrete steps. Here's a simplified simulation of how a leader detects and fixes a follower's conflicting entry. The article says almost never, but there are niche cases. If you need to implement a custom consensus layer and require optimal performance under high contention, multi-Paxos can be more efficient than Raft because it allows multiple leaders, though rarely used. Also, some legacy systems like Google's Chubby use Paxos, so integration may force your hand. The article's triage section lacks a concrete command to check election timeout configuration. Here's how to verify it in etc. Here's a debugging guide. First, check network connectivity between nodes. Verify election timeout config is greater than RTT. Check for clock skew. Restart nodes one by one to force election. Use these commands to diagnose. Let's run through some common interview questions. How does Raft handle leader crash after commit? Client retries, new leader has committed entry. When choose Paxos over Raft? Almost never, only if existing Paxos infrastructure. What happens in partition of 5-node cluster? Majority partition makes progress, minority unavailable. And a few frequently asked questions. What is the difference between Paxos and Raft? Paxos is hard to implement, Raft is understandable. Should I use Raft for new systems? Yes, it's easier and well documented. How to configure a Raft cluster? Use odd nodes, set timeouts, enable log compaction. Key takeaways: Raft is the consensus algorithm you should use for new systems. Always use an odd number of nodes. Log compaction is not optional. Consensus is expensive. Don't use it if you can tolerate eventual consistency. Ready to go deeper? Up next, leader election, then quorum, R plus WN, then distributed transactions, and 2PC. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.